Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're going to be doing our third lesson in predicate logic. We'll be looking at the change of quantifier rule. So, welcome back everyone here. I hope you're doing well. Let me start off with a brief review. I've actually typed up a couple things here that I want to sort of take a look at here with you. Just to start off, right, the first thing, what we've been doing in predicate logic is essentially building proof sequences. And, right, we've been doing these proofs that look sort of like geometry proofs, but in particular, they look very, very similar to the proofs we looked at in terms of propositional logic and natural deduction. So the difference, though, is that in predicate logic, we had to introduce, we introduced the quantifier. Now, the quantifier allows us to actually analyze statements that make categorical claims. Claims like all monkeys are animals, and right, and some people are jerks, and things of that sort, right? But we have two types of quantifiers, right? The first type of quantifier we have here is the universal quantifier, and basically we symbolized it like this, where you put an x in parentheses in front of a statement function. Now, one thing I should mention, I didn't mention in the video, is that we're using the Patrick Hurley textbook, and this is the way he does it in that textbook. But if you look at, most people do make a universal quantifier looks like this, with an upside down a and an x. So some of you, if you're looking at other YouTube videos or whatnot, you're seeing this, you're probably wondering what's happening. The reason that we're not using that symbolism is because it seems unnecessary for what we're doing here in terms of just learning the concepts. So Hurley doesn't think it's necessary with the sort of basic introduction level. Ultimately, you could write it like this if you wanted. The second type of quantifier is the existential quantifier, and it looks like a backwards e x in parentheses in front of another statement function. And so this says that this basically makes a universal claim, and this makes an existential or a particular claim, okay? Now, we also introduced this, right? And you probably can't read this writing right here, so just don't worry about it. But there was a problem ultimately, and the problem was that in order for us to use the rules of implication and inference, things like modus ponens and modus tollens, in order to build our proof sequences, we had to introduce rules that allowed us to remove and then insert quantifiers, because you can't utilize those rules of inference if you have a quantifier in front of it. So we introduced these rules. We have to remove a quantifier, we called that an instantiation rule. There's a universal and an existential instantiation, and here's what they basically look like. And the way you read these is you start from here and you move to this one, right? So if you have a universal statement like this, you can always instantiate it, demonstrate an instance of it by removing the quantifier and keeping a statement variable, keeping variables within the predicate statement, or to instantiate, you can give it a particular name. Remember, x, y, and z, we've reserved these three variables in order to always represent essentially anything in the universe, whereas all of the other letters, right, a through w here, these represent particulars, right? So this is our first rule for universal instantiation. In terms of existential instantiation, you can see that if we have an ex fx here, we can always instantiate, but we have to instantiate it with an fa, but a has to always be a new name within the proof sequence. That's a pretty important rule. But here's the thing. If you have an ex statement, you cannot instantiate it to a variable, a statement variable. You have to go with a new name, okay? Now, once you've instantiated and removed those quantifiers, you may, in the proof sequence, actually have to reinsert them or generalize them, okay? And here's what the generalization looks like. If you have a universal generalization, you have to begin with a variable in order to add that universal quantifier. You cannot, this says not, you're not allowed to generalize from a statement name, right? So if you have FA, you cannot generalize that into a universal. But you'll see that if you have FA, you could generalize it into an existential generalization. Oops. And that's what this is right here. You can also, if you have Fy, if you have a statement function with a variable, you can generalize it here existentially, right? So you're not allowed to do this, and you're not allowed to do this, and you always have to give a new name. But otherwise, we introduce these rules in order to allow us to remove and insert quantifiers. So that's sort of this brief review here in terms of the quantification. And if you need to, take a look at our video 8.2, which overviews this in a much slower fashion. There's still a problem, though. And here I've written up a little problem for us. And it looks like this, because one of the rules we talked about is that you cannot instantiate a negated quantifier, right? That was one of the rules actually we talked about in our earlier videos. And the reason you cannot instantiate a negated quantifier is because, remember, a quantifier is making a categorical claim, but if you're making a categorical claim that something is not categorically the case, you can't instantiate, meaning you can't demonstrate an instance of something that's not the case, right? And this goes all the way back to a very old philosopher by the name of Parmenides. Here, and Parmenides has this argument that says something, what is, and what is not, and we could go through the metaphysics of that, or you could look that up on your own. But ultimately what it means, though, is that you cannot show that something is, when we say something is not the case, we can't show it's not the case by saying that something is the case, right? Nothingness cannot be somethingness, and somethingness cannot be nothingness. That doesn't make any sense. Or at least for our case, right? Nothingness, right, cannot go, it cannot go into somethingness. So, right, so if I say it's not the case that all dogs are reptiles, right? I can't instantiate that statement. I can't show you an instant or demonstrate an instance of something that's not the case, because you can't show something from nothing. So that means over here we have a big problem, right? And our problem with this problem is, what happens if we have statements like this? Because guess what? We do in fact make arguments with claims like that. So what we're going to need to do is we need to introduce a new set of rules to change these quantifiers, to get rid of these negations, because we'll see that if we could put the negation in front of the statement function but not in front of the quantifier, we could demonstrate an instance of it. So that means, let's take a look at here. Right, I guess that's as big as I can get it for you. Right, I've written out here 4 different phrases, 1, 2, 3, 4, and these are going to turn out to be verbal forms of 4 change of quantifier rules that we're going to introduce in our video today. And they basically work like this in terms of ordinary language. If I say everything is wonderful, that essentially means the same thing as saying it's not the case that something is not wonderful, right? And if I were to write this out in quantification logic, it would look like this. X of fx is logically equivalent here to saying that it's not the case that something, right? That would be my existential quantifier, is, and then I negate the statement function. That's what that looks like there. So, and because these are logically equivalent, what it means is that if I have a statement like this, I can switch it out with this, and vice versa. So I can change out the quantifier, and when you change the quantifier, it becomes a sort of formal mechanism that will allow me to then use my instantiation and generalization rules in order to actually build out the proof sequence. So look at the second one here. It's not the case that everything is wonderful really means the same as something is not wonderful. So what would that look like? It would look like this. It's not x of fx. That's logically equivalent here to saying that you have something is not wonderful. right? And you can instantiate this because the quantifier is not what's getting negated, it's the statement function. And we never had a problem with that before. It's only these quantifiers that can't get negated, okay? So if I have a negated universal, all I need to do is swap out the universal with an existential quantifier and move that negation in front of the statement function instead. Okay, now look at the third one. Something is wonderful is really logically equivalent to saying it is not the case that everything is wonderful. So something is wonderful, what does that look like? Well, that would be an EX, FX, and that is logically equivalent to saying it's not the case that everything is wonderful. Okay? Oops, there's a little mistake here. I should have said, oops, it should say it is not the case that everything is not wonderful. Okay, let's edit that right now. Little typo. Okay. Okay. So something is wonderful is logically saying it's not the case that everything is not wonderful. Okay. So let's take a look at this the fourth one here. The fourth one says it is not the case that something is wonderful. That really means, well, everything is not wonderful, doesn't it? So that looks like this. It's not EX, FX is logically equivalent. And remember, the double colon here means logical equivalence. It means that everything, well, is not wonderful. So it looks like this. It's not FX, okay? And so we have, these are going to be our four change of quantifier rules, right? And so you can see here that if I have a negated existential quantifier, I can do this to it, and it'll work out. But it means I have to delete the negation in front of the quantification, change the quantifier, and then reinsert a negation in front of the statement function. And it works the same way with all of these, except sort of inverse here. So if I have this, I can switch it to this. If I have this, I can switch it to this. And if I have this, I can switch it to this, right? Now, what's important here, though, is I have to move the negation. But if I start with this, I have to have a negation in front of that function in order to get here, okay? So these are our change of quantifier rule. And if you took a look at the textbook, let's see, where is it here? Here's what they're going to look like right here, okay? These are the essential rules. Now, what you really need to do is you need to basically memorize these and or make sure that you have these on a note card or something while you do your homework exercises or anytime you actually build out a proof. Okay, and we're going to see that obviously since we've just started predicate logic that these aren't going to be sufficient for every sort of problem either, but it will allow us to solve a lot of problems, okay? So let's take a look here. Let's move these over. Actually here, you know what we'll do? Right, because these are the rules. Let's just delete those. We don't need these. Right, but here's our change of quantifier rules, and we'll just sort of put them, whoops, let's move them over. Oh, some reason it won't let me. Okay, there we go. So let's just move these over here, and now let's go back over here to our problem, okay? To this problem, because remember we said with this we argued that we have this problem, right, we have to get rid of these change of quantifiers. So let's do the proof of this problem and see what it's going to look like, okay? Actually, here, let me pause the video and I'll pull these up on the side so we can look at them while we're doing it. So give me just a second here to pause the video. Okay, so here we are, we're back. I've just actually copied and pasted this here so we can look at these quantifiers as we're doing this problem, okay? So let's, our line 3 here. What we need to do is we need to remove both of these quantifiers, right? Which one should we start with? Well, it doesn't actually matter which one we do when we change the quantifier. So let's start with the first one here. You can see I have a negation of I have a negation of an existential quantifier here, which is this sequence right here. which means that if I'm going to change the quantifier, it's going to look like this, x with the negation in front of the statement function. So let's do that now. That's going to be x of the negation, what is it, of px and negation of qx. Okay, and then we'll close that off, and that's going to be line 1. And all you need to write here is CQ for change of quantifier. Okay, so let's look here at number 4. Alright, hold on a sec. Hi everyone. Sorry, I had to pause the video and rewrite the problem. For some reason, I was using Adobe Illustrator, and Adobe Illustrator started slowing down on me, so I just decided to rewrite the problem here. So let's redo it here. So let's do the change of quantifier again on line 1, which is going to turn into this section here. So that's going to be x, the negation of px and not qx, right? And all we do is write line 1, CQ for change of quantifier. Okay, that's all we need to do for that first problem, that first line. Now we've changed the quantifier. Now line 2, let's take a look at that. That's going to be line 4. Now I just have to look for something like this. This is not negated in front, so which one does that fit? That's the negation of x of fx right here. So that means it's going to switch into this, which is going to be an existential quantifier. And then I add a negation, or I really move the negation, to not Rx or Qx. And that's line 2, change of quantifier. Okay. Now that I've done that, right? So now that I've done that, I can obviously begin to instantiate it, but I want to show you something real fast here. In our last video, we talked about the rules of implication. We can also take a look at the rules of replacement. The rules of replacement are not bound to the quantifiers. Remember, the rules of replacement state that you can switch out a part or an entire section of a line, which means that we could actually do a De Morgan's here if we wanted. Okay, you can do a De Morgan's on lines 3 and line 4 if we wanted. We could also wait and do the De Morgan's afterwards. It doesn't really matter. Well, it may matter, and this problem I don't think it matters so much. So let's go ahead and do our existential instantiations here. Now remember, if we're doing that, which one, here's where it matters. Should I do the universal instantiation or the existential instantiation first? Well, remember, if you do an existential instantiation, you have to go to a name, right? Which means that if we have to go to a name, then what I need to do is I absolutely need to do the number 4 first. So let's do that. So an existential instantiation of this is we're going to have to give it a letter. We'll give it the letter A. So that's going to turn into not R, A, or Q, A, right? That's line 4, existential instantiation. Now that I've done this one, and this is the first time that A has existed in the proof sequence, now I can do my universal instantiation. And I'm just going to go to the letter A as well. So that's going to be line 6. Right, that's going to be not PA and not QA, and that's line 3, universal instantiation. Okay, now that I've done that, of course, I have these negations, and now I really just need to do De Morgan's on each of these. I could have done it previously, but I didn't. Not a big deal. So let's do the De Morgan's on line 5. So that's going to be not RA, and remember the sign switches when you move in that negation with De Morgan's to not QA, right? And that's line 5 De Morgan's. Line 8, let's do a De Morgan's on line 6. So that's going to be not PA, right? Or not QA, right? And that is line 6 De Morgan's. You can see I have these double negations, so we got to get rid of those too. So line 9 here is going to be RA and not QA, right? And that's line 7, double negation. Line 8, I have a double negation here, so I need to get rid of that. So that's going to be line 10 is not PA or QA. Okay, that's line 8, double negation. Now, what are we looking for here? We need to get not PX by itself, right? But in order to get it by itself, we need to, right, we're going to have to, looks like we have a PA here, so we need to get this thing by itself. So just so you can see how we're doing the problem, we need to get this by itself. We have a not QA. We could do a disjunctive syllogism here. So line 9 here, I have to actually commutate and simplify. So line 11, I hate the commutations and simplifications. It takes up a lot of time. So that's going to be not QA and RA. That's line 9, commutation. 12 is going to be simplification, not QA, right? So that's going to be line 11, simplification, right? Now, of course, I have to commutate this too. So line 13 is going to be QA or not PA. That's line 10, commutation. And now I can use this disjunctive syllogism because this says if I have P or Q but I don't have P, I must have Q, right? So line 14 here is going to be not PA, right? 12 and 13, disjunctive syllogism, right? And now that I have this, not PA, I can now generalize, do an existential generalization of this, right? Remember, the existential generalization, you can go from either a variable or a name. We have a name because we had to do an existential instantiation. So this is going to be EX, not PX, right? And that's line 14, existential generalization. And that's the proof sequence. You can, here, I'll zoom out and you can take a look at the whole proof sequence here. Right, fairly long actually, but it wasn't difficult in terms of the logic. It was just we had to do the De Morgans and the commutations and simplifications, and you could have done those in different orders. But that's essentially how we do this sort of problem using the change of quantifier rule. So let's go ahead and take a look and see what other problems we can do here. Let's take some from the book here. Oh, you can see, I think this is the same problem we just did. So they just did it the exact same way. Let's do this problem. Let's not look at it. Let's rewrite. Actually, I'll just rewrite it over here. File, new. Okay, so let's take a look at this problem. This problem looks like. Should we get this? And I'll only do 2 more problems for you because the change of quantifier rule is really not too difficult here. But it's going to look like this. We get, whoops. Right, if we had EX. I keep saying EX, but really I mean existential quantifier. HX and GX. Then X of LX. Line 2 here is you do not have LM. So therefore you have X. I'm sorry, the conclusion you're looking for is X of HX. Then I'm running out of room, GX. Right, so that's the problem we're looking at here. So we need to get to this where we have a universal HX to not GX, which basically says no H or G in the long run right here. That's a no SRP sort of quantified statement. Okay, so let's do this problem. How can we do this? You can see here we have two quantifiers here combined. This is sort of a problem. What should we do? Since the conditional, one thing to notice is since the conditional is not trapped, if we did have this, we could get this, and we could use a modus ponens without changing the quantifier. But I'm not sure what to do. We have an L, we have not LM, so you could see here if we could generalize this, we could maybe do a modus tollens to get this thing by itself, but you can see we have a conjunction here. What are we supposed to do? Well, let's start off by doing, I think, an existential generalization of this statement. That seems to be the best bet here. Because I'm not sure how else to work the problem until we get this thing generalized. So if we do an existential generalization, it's pretty simple. It's going to look like this. EX to not LX, right? So now it looks like this, but you can see here this is an issue for us, right? So that's line 2, existential generalization. But now that I have this, can't I use that change of quantifier rule again? And I think I deleted it, but you can take a look at it. If I have a statement that looks like this, I can actually change the quantifier, but you're going to end up with not x of Lx, right? So that's line 3, change of quantifier. Now you can see here, now I can do a modus tollens, obviously, right? Because now I don't have this, which means line 5 here is going to be you don't have Ex, Hx, and Gx, right? You don't have this thing. That's line 1 and 4 modus tollens. Okay. Now that I have this, right, of course, it looks like I have to do another change of quantifier again. So what is that going to look like if I do the change of quantifier? Well, what I'm going to end up with here is I'm going to end up with x. I'm going to switch out the quantifier and then move the tilde in front here. So I'm going to end up with x of not hx, right, and gx. Right, that's line 5, change of quantifier. Right, now that I've done that, what was the problem that I needed? Oh, you know what I'm going to need to do here? I need to do a De Morgan's, right? And I can do the De Morgan's in here because that's a rule of replacement, which means I don't have to touch the quantifier. But that's going to end up with not, I'm going to put the parentheses back here because remember this whole thing is applied to this whole sequence. And so I need to keep the parentheses there. So that's going to be not hx or not gx, right? That's line 6 to Morgan's. Now, do you recall this, right? What can I do here? Is there a rule that if I have a disjunction, a rule of replacement that will allow me to switch it to a conditional? There is, in fact, if I have the negation in front of this part. So that's the rule of implication, which means I can get x, right, hx, then not gx, and that's line 7, implication, right? And of course, that is the conclusion I was looking for, right? So this problem, though, I like this problem because this problem didn't require us to actually do any instantiations or generalizations. Well, no, we did do one. I'm sorry. We did one existential generalization. But we actually just worked with the problem using the rules of replacement with the quantifiers in place, okay? So, and that's how you do these problems. It's really not too difficult. You just have to, it looks like a lot, but that's why we've been moving ever so slowly in this course program here so that you can get a handle on these. So let's do one problem here from the homework. Let's sort of scroll down here. I'm going to take a look at the homework. Let's do problem 2. Let's see what we can do with problem number 2. We know here, I'll just, well, let me copy it, snip it. So let's do this problem here and see what we can do with this. Okay, so let's do this problem. And I don't have them here. You can't see them, but I have the rules all in front of me while I do this. And what I encourage you to do is pause the video, try to do this problem, and then see how I did it and see if you can see what we've done. Again, always start by looking at the conclusion. I need a negation all AX here. So you can see where's my AX? It's right here. So I need to do a change of quantifier at some point to get this sort of thing. You know, I have a BX here. I bet we're going to do a disjunctive syllogism, do a change of quantifier here, a disjunctive syllogism, which will give us this, and then we'll do another change of quantifier. I think that's what this problem is going to look like, but let's try it. So line 3 here, let's do a change of quantifier on x of bx, which is going to look like this, to the negation of ex, negation bx. That's line 2, change of quantifier. Of course, this looks just like this right here. What I need to do is I need to commutate these things before I can do that disjunctive syllogism. So line 4 here, I'm going to do ex negation bx, or existential quantifier negation ax. And all I did was line 1 commutation. Now line 5 is if I don't have this, right, which is this right here, that means that I'm going to end up with this right here. So that's going to be ex negation ax, right? And that was line 3 and 4, disjunctive syllogism. And now that I've done, now the reason I could do the disjunctive syllogism again is because that disjunction is not bounded by a quantifier. If it was, I couldn't do it. I'd have to actually instantiate first. So now that I have this, I think what I'm going to need to do is change the quantifier back to this. And I think I'm going to end up with this right here. So that's going to be line 6. If I have ex here with the negation, that's going to turn into the negation of x ax. Right, and that's line 5, change of quantifier, and of course that is the conclusion, so that's the proof. Okay, so you can see these problems aren't too difficult. What it requires ultimately is that you've gone through and that you've slowly built up your skills in order to see substitution instances, because this definitely looks like a lot of symbols on the board here. But hopefully by this point you're in good shape here. Okay. So that's how you do the change of quantifier rule, okay? And you can see that the problems, they get complicated, but ultimately the argument, nothing really changes in terms of you've already been using the rules of replacement, the instantiations, and the generalization. So you're already good shape for this. The change of quantifier rule just gives you that one more tool you need in order to do these problems, okay? Well, that concludes our video for today. Thank you for watching, and I look forward to seeing you guys online. Okay, bye.